All right. Hello, ladies and gentlemen. Good morning and good afternoon. I'm so happy to be here as a part of the group that I have honor to be here. So, first, we want to talk about a new method in additive manufacturing of liquid crystal elastomers that is melt electrowriting. So let's start with a very principal thing that is soft actuators here. They are polymeric systems that can be deformed via the external stimulus, something like light, temperature, pH, humidity. And also we have soft robotics here that can use soft actuators or not. That the difference between hard and soft robotics, they are flexible, kind, friendly, and deformation much better than hard one. We are using in plenty of materials in soft robotics like hydrogels, like thermoplastics. And one of them is liquid crystal elastomers. For the people, if doesn't know liquid crystal, what is liquid crystal? Liquid crystal exactly is the thing that your computer manufacturer has used that to watch this screen, this presentation via your screen. Liquid crystals always has a core that we call it mesogens. And these molecules, these mesogens, if we want to connect each bottom of them to the other one, we can make a chain. And if we want to connect all the chains together, the neighbor chains together, we can make networks and then elastomers. So this is one important thing. And the second one that is very important too, all of the mesogens should follow one specific direction. So if we apply external stimulus to that, like temperature, like electricity, they can reorient. And we can say that they are going from isotropic phase to anisotropic phase. We will continuously talk about this phenomena. So what if we want to use this phenomena in the field of 4D printing? Several years ago, in independent research in 3 places that happened by Jennifer Lewis, Professor Jennifer Lewis, Professor Taylor Ware, and Dr. Carlos Sánchez-Somolinos here, they introduced a method to align the liquid crystals using direct ink writing and bringing it to the 4D printing area. So the alignment of liquid crystals, we talked about the chains. Long axis of the chains should be in parallel of the direction of the printing. For example, here, we can see that in the direction of the printing, long axis of the chains should be parallel. In this image, this is a homemade 3D printer that we are using here. In this cartoon, we can see the principle of the printing using liquid crystal elastomers, and this is the starter of the field of liquid crystal elastomers for the printing of liquid crystal elastomers. So the method that is happening with DIW, first, one layer is printing, then UV radiation in order to make crosslinks, then turn that polymer to the elastomer, that network to the elastomer, then second layer, then again UV. So in this case, we will have different layers. And as we talked before, the principle of this method is alignment. So in our previous work, in the test of muscle tension and the test of cone deformation, by applying the temperature, it is totally working. So this means that this technique is useful with liquid crystal elastomers, digital deposition. But there is one problem with DIW, and that is the order of the fibers are in the terms of microns, hundreds of microns. The minimum amount of that can be 100 micron or 150. So how we can fix that? There is one way. If we can decrease the pressure in DIW and increase the height of printing, I mean the nozzle, the distance between nozzle and the printing platform, but we can't have any fiber because of a phenomena that's called Plateau-Riley instability. That says if we have a narrow share of a liquid, because of the capillary force, it can be cut and turns to be something like droplets, like here. So how we can overcome to this? We can use a help here that is, in our case, electric field. We can apply charges on the surface of that material, and by applying charges, we can have field, electric field. So the technology that uses this phenomena, applying electric field to the narrow share of a material, is melt electrowriting that has been developed by Professor Hutchmer from Queensland and Professor Dalton from Oregon. For the first time, we introduced melt electrowriting of liquid crystal elastomers. And if you see the principal printing mechanism of this melt electrowriting, we have a UV light here that is curing our fibers upon they touch to the ground. And also we are using air pressure and heater that was in our case 60 degrees Celsius and a high voltage collector. Our plate also a high voltage source and our plate as grounded. So one important difference in between DIW and MEW is the fiber fabrication process and stabilizing. First, we are applying an electric field, a proper electric field here. Then our droplet goes down. Then we should have a lag of fiber. As you see here, this is the video speed has been doubled. Also, there is another important thing that happens that we should pay attention to that in melt electrowriting, and this is small area. Yeah, that is called Taylor cone. This Taylor cone shows and determines the thickness of each fiber in your printing section. So, excuse me, yeah. Here we can see a cartoon that shows the fiber deposition and the printing method in the melt electrowriting. In DIW, we are almost touching the ground, but in melt electrowriting, this is the normal way that we should print, and we are using the lag of fiber. Like again, DIW, we have several parameters here, like speed. By increasing the speed, we are decreasing at the same situation, same parameters. We are decreasing the thickness of fiber. By increasing the pressure, we are increasing the thickness of fiber. But by increasing the voltage, as I told before about Taylor cone, by increasing the voltage, we are decreasing the area of the Taylor cone. And this Taylor cone can act like a source of material. When the area of Taylor cone decreases, the thickness decreases. So again, we have to talk about the alignment of the fiber. The long axis of the chains should be printed in the parallel to the direction of the printing. We have here a 25 micron liquid crystal elastomer printed by melt electrowriting fiber here. And for proving the alignment, we used a polarized optical microscope. In the 0 degrees, that the observer polarization was perpendicular to the long axis of the fiber. We can see almost nothing. But in 45 degrees, we can see the fiber, and this shows this alignment is much better than other techniques. So also in the alignment mechanism in melt electrowriting in the cartoon, we can see that it's almost like DIW, but we are printing much more thinner fibers. So as a start of proving that liquid crystal elastomers are compatible with melt electrowriting, because the main material for melt electrowriting is a thermoplastic that's called polycaprolactone PCl. But here we wanted to say that liquid crystal elastomer can be usable with melt electrowriting. So the primary scaffolds and structures for MEW are grid structures because they are usable in tissue engineering. So we used two different types of nozzle, 250 and 100 micrometer nozzles. So here we have fibers with the thickness of 25 microns. The area between two fibers, the period is about 300 micrometers, 4 stacked layers, 4 plus 4 in the junctions, about 8 fibers. So also we have another scaffold here that the period is 90 microns. Each fiber can reach to 15 micrometers and 5 plus 5. And also another scaffold that the period is 350 fibers plus 50 fibers. Each fiber thickness is about 8 microns. So this is easily possible, and this shows that high aspect ratio, thinner fibers, higher walls is possible with melt electrowriting of liquid crystal elastomers. But for going to soft robotics field, we need to print another type of structures, open pore and auxetic structures. So we started again with another type of designs that here, the sinusoidal design, each line contains 5 stacked layers on top of each other. The thickness of each fiber is about 60 microns in the junction, 15 fibers on top of each other. And also the same design with 16 micrometer fiber thickness. That was possible easily with melt electrowriting. So again, the actuation process. Again, we are going to the alignment. That is very important in liquid crystal elastomers. This is, let's imagine that this is our printed fiber. All the chains are, long axis of the chains are parallel to the printed fiber, the long axis of the fiber. By applying the temperature, they start to reorient. We have the same amount of molecule at the same place, but they are going to reorient. So the fiber goes to be shorter, but the width should go to be expand. So for example, here we have a sinusoidal design 3 plus 3, and by applying the temperature, it starts to deform in 120 degrees Celsius very easily. Also, we have another type of designs here, like famous reinterred honeycomb, antichiral and chiral structures, and also those 16 micron fibers that was totally actuated inside the liquid, inside the water. So our material also compatible with actuation inside the liquid. Also, we have a video here of the actuation of 3-layered antichiral scaffold. The speed has been doubled, but this shows that the melt electrowritten liquid crystal elastomers are reversible in the actuation. They are going back again many times and without any problem. So also we needed to see the efficiency of our scaffolds, our structures, working capacity. So we designed a semi-spider web-like scaffold with liquid crystals, 4 layers, and we put a steel ball that was 370 times heavier than the weight of a scaffold. and it started to push it up easily. So this can show that according to that high level alignment of liquid crystals, these very narrow structures, narrow fibers, can hold this amount of weight here. And as a conclusion, melt electrowriting can easily fabricate micron scale liquid crystal fibers. That is challenging with comparing other methods. And the Taylor cone in the in the melt electrowriting plays very important role that can be changed by voltage, especially, and also with other parameters. We have group of parameters like DIW, but a bit more than that. By aligning mesogens parallel to the fiber's axis, we can gain precise control that is response to mechanical response to the temperature. And with melt electrowriting, we can reach to small periods easily, high aspect ratio, and thin fibers up to 100 layers. And also, this is very challenging by using by other additive manufacturing methods. And these structures can show controlled deformation upon heating and remarkable capacity efficiency, capacity mechanical work efficiency. And I want to say thanks from the organizations and the projects that help us to make this journey happen. And at the end, thank you so much for your kind attention. In this picture, as a hobby in the lab, we prepared a 5-layered spider web-like scaffold. By the way, I'm so sorry, our spider has had a little bit disability here, but each fiber here, each line here contains 5 layers on top of each other. So at the end, if you want more details about that, I invite you to see our recent publication. And thank you so much again for your attention.